So binary operations are the idea of manipulating the bytes at the bit level. And everything you see on a computer, I don't care what it is. I don't care if it's this image that you're seeing, the characters on the screen. Everything breaks down to some kind of electrical circuit that is a series of bits, and those bits can be turned into bytes, and those bytes can form larger data structures. It's, if you think of it like, well, I don't know what bricks are made of, so I'm stepping out of my element, but let's just say that bricks are made out of sand, and each one of those pieces of sand makes up the brick, and then you can take the brick and build houses, chimneys, anything you can think of with the bricks. Or maybe you don't make bricks, you build something else. So the bits are at the heart of everything. So before we get started, let's talk about binary math. And binary math is something that trips up a lot of people new to computer science. And in reality, binary math is really not that complicated. It's not as complicated as it seems. Think of it like this: if you had something and you had to represent numbers, and the only thing you had was, let's say, for example, you had 10 lights, and better yet, 8 lights, because that composed a byte. So let's say you had 8 lights and they could only be on or off. So on or off can be represented by 0 or 1, 0, 1, 0, 1, or 1, 1, 1. But you can only be on or off. That's the reason that you have only zeros and ones, is because it is binary, because they represent an on state or an off state. And that is the best way to represent something, with an on state or an off state. Now, with electricity, you can potentially measure different ranges of electricity, but that would be really difficult to do, because what would each thing mean? Now, in the decimal number system, we have the luxury of having 0 through 9, and we have positions. So in the decimal system, we have, for example, we have a value, and let's say, for example, I say 999. What is the greatest number that 5 digits can give me? And that value is 99,999. You cannot get to 10,000 because you would have to add another digit. Well, with binary operations, it's the same way, except we have 1, 1, 1, 1, 1. 1 is the greatest number, and you notice it's also an odd number, and it only goes up to that. Because if I convert any of these to 0, it's 0. Now, in binary operations, it's really interesting, because it and what you see here, the 1, where you see this number doesn't really represent a 1, because it is a base 2 system. So it is a base 2 system. And what does that mean? Well, the decimal system is a base 10 system. So what happens is, in the case of 9,000, let's not go all the way up to 9,900, 900. Let's just go into that. We have a 9 in the ones place here, and we have a 9 in the tens place, and a 9 in the hundreds, and a 9 in the thousands. The way you can compute this math is if you said, for example, 9 to the 0 power, and we'll use this representation, 9 to the 0 power plus 9, right? Not, well, 9 times 10 to the 0 power, excuse me. It would be 9 times 10, 9 times 10 to the 0 power, and any number to the 0 power is 1, so it would be 9 times 1, right? 9 times 1 to the 0 power, and 9 times 10 to the second power, or to the first power. Let's see, 9 times 10 to the, and I can't find my head operator, so 9 to the ones power, 9 times 10 to the ones power, so this is 9 times 10 to the 0 power is 9 times 1. 9 times 10 to the first power is 9 times 10, so that's 90. And then we do another one, 9 times 10 to the second power, and that gives us 10 to the second power. As you know, 10 times 10 is 100, so 9 times 100. And so then plus, and I forgot my plus symbol here, and that now gives us 9 times 10 to the third power, and 9 times 10, 10 to the third power is 1,000. 10 times 10 times 10 is 1,000. Well, base 2 operations are no different. What I have, the number that I have here, and even though I'm going from left to right, I'm really taking the first number, the leftmost number, the least significant number, and doing that, and then working my way this way. So I'm working from, in this case, right to left, but I'm actually computing it to left to right. So what I would have here, for example, is something similar, but in this case, we have 1 times 2 to the 0 power. And so what is the number? 1 times 2 to the 0 power. So it's 1 times 1, because any number to the 0 power is 1. And then we have 2 times, 1 times 2 to the first power. So 1 times 2, so it's really just 1 times 2, which gives us 2. And we move on and we say 1 times 2 to the second power. And 1 times 2 to the second power is 4, so that's 4. And then you go to 1 times 2, and we end at 1 times 2 to the third power. So 2 to the third power, as you know, is 2 times 2 times 2, which is 8. So we have 8. So this looks really confusing, I know, just bear with me. But if you take this is 9, this is 90, this is 900, and this is 9,000. You add them together and you get 9,999. Well, this is very similar in essence, because you have 1. This is in the ones place. This is in the twos place. This is in, it just, you notice it just doubles every time. 1 and 2 and 4 and 8. When you add those values together, this gives you the value 15. So if you take that 15, you can take that value 15, and that's the way it's represented. And then you can take, if you were to add another more out here, then you would have more numbers, and it would be a much bigger number. So it'd be, it stopped at 8 here, because we go 1, 2, 4, 8. And then, of course, it would be, 16 and 32 and 64. And if you ever wonder why all your memory and those kinds of things are always like 32 megabytes, 16 megabytes, 32 gigabytes, 64 gigabytes, and so on, it's because it's all binary, and that's the way it's done. It's just done in groups of binary. So, with that said, you can represent a lot of numbers. So here, with these numbers alone, I can combine them. The combination of turning them on or turning them off, I can have 16 different values. If, for example, if I did it in order, I would do 0, 0, 0, 1, 0, 0, 0, 2, right? But that's not a 2, that's a 2. And then 0, 1, 0, well, actually not yet, because this would be 3, because 1 and 2 is 3. And then 0, 1, 0, 0, which would give me, this is the ones place, the twos place, and the fourth place, so that would be 4. And you get the idea. Now I got 1, and then I add 1 more, and now that's a 5. So this is 1 in decimal, and this is 2, and this is 3, and this is 4, and this is 5, and if I wanted 6, well, I have to put a 1 in the fourth place, a 1 in the twos place, and 0 there, and it's 6. And you notice something else interesting, that every number that ends with 0 is even, and every number that ends with 1 is odd, because that 1 in the ones place is going to make it an odd number. So I can go all the way down, and eventually I'm going to get to where I have all the ones on, and it gives me the value 16. So I can say here, for example, ... 1, 1, 1, 1, and get 15, because it's going to be odd. So it's 16 values because we actually didn't start from 0. Everything in most programming languages starts from 0, and that 0, all zeros across is 0. Gives us 15 possible values, and it gives us that. There is more computer science to the way numbers are stored, but we don't have to really concern ourselves with that. One thing we do have to concern ourselves with is if we want to manipulate these different bits, what do we do? So there are some simple operators that allow us to do that, and I am going to be talking about them. This video may run a little long because I'm going to cover them, and also I am rusty in these operators, so just bear with me. You don't normally do this in most programs. You may have to at some point or another for very specific reasons. For the most part, you don't have to. So the big takeaway from this is that they are there, and if you want to do something with them, you know they're there and you can use them. So we are going to talk about them. So first one on the list is the binary AND. And this binary AND, what it does, if you have these bits, right? So if you have 0, 0, 0, 0, 1, 0, right? And you do this operation and you do 0, 0, 1, 0, then they are, it means that what would come out of here would come out 0, 0, 1, 0. And you say, well, okay, that doesn't make sense. Okay, what about if we did something like this? If we did 0, or let's just do 1, 1, 1, 0, and 0, 1, 0, 0, what comes out of it is 0, 1, 0, 0. Ooh, what happened there? So basically what's happening here is that it's taking these values, and to help illustrate it better, let me put another line here, and let me put another line here, and let me put another line here. What happens is it takes the values and it looks at these two numbers, and wherever there's two ones that match up, it will return a 1 there. So now with the other example, let's take another example and we do this and the binary and what you get is we take this value, the first value, and we take the second value. 1 and 0, well, that doesn't work because one is a 0 and one is a 1. And this one, both of them are 1, so it gives us a 1. And this one is 1 and 0, that doesn't work. And both are 0 here, so there's not a 1 there. Both have to be a 1 in order for that result. What if we had another one? Let's say we had a 1 here and a 1 here. Well, the result would be that because it compares to that, right? But if we had, for example, this value and this value, oh, oops. We have a different set of values. Well, this is a 0 and this is a 1. That's not compute to 1. These two compute to 1. This 1 and 0 compute to 0 because they both have to be 1s. And this one compute to 1s. And so that is your AND operator. If we want to see it in action, let's take, for example, let's go and do an operation. So let's go ahead and do a printf. And I have my sticky mouse situation. So let's go ahead and do a printf. And we say, let's take two values, right? So we took two values, right? And we looked at all these values. And we know this is the value for 5. And we see here the value for 6. If we took those two values, 5 and 6, it's going to give us a 1 here. Not a 1 here because they're both zeros. Not a 1 here because they're both zeros. And not a 1 here because they're both zeros. So what it's going to give us, the value here. And what value is that, right? So what the value that it's going to give us, you notice it's going to give us 0, 1, 0, 0 because this is 0. This is 1. This is 0 also, and this is 0. So 5 and 4 make 6. And it's basically the intersection of 5 and 6. Where do 5 and 6 intersect? Well, the commonality is that they both have the same value. If you're not familiar with this, it would be akin to saying, for example, in the decimal system, if you had 0, 9, 1, 9, and you have the same value for those two decimals, so you would have a true here and a true here, but these ain't true because they're different. Now, in the decimal system, you typically don't do that. It would be a lot more challenging to do it because it works a lot different. but with bits, it works this way, and you have this where they intersect. So let's take a look at that. And it's very simple how we can prove it, because we can take the value 5 and 6, and it should give us 4. So we can say 5 and 6 is, and we won't print out the result, we just put it %D. So once we have 5 and 6, it should give us 4. And let's see if it does that. So we take the value 5 and 6, and we run it, and let's see what it gives us. 5 and 6, what do you know? 5 and 6 is 4. Let's take another value, another example, and we can take 3 and 4, for example. And you notice 3 and 4 don't intersect anywhere, because 0 is 0, 0 and 1 is 0, 1 is 0. So 3 and 4 should give us 0. So it's going to give us a 0 because they don't all match. So let's just take that example and copy this and paste it. And so if we take, what did we say, 3 and 4? If we take 3 and 4, the values 3 and 4, and we do a bitwise and it should give us 0. And it does. So hopefully you get the picture with that. Okay, but there may be situations where you want to join things together and you want to have multiple values. Let's say, for example, that we had something where the colors, we could have several options, right? Let's say we had an option, and our option was that we had, let's take an int, and let's take 0, let's take 1, right? Let's take 1, and that is equal to, let's take blue. Oh, I'm sorry. I always hit my page up. Let's say that is blue, right? Equals 1. Let's take our primary colors, and let's say blue equals 1. And let's take red, and red equals 2. And let's take, what's our other primary? Red, green, blue. So red, no, is it red, green? It's not green, that's yellow. So in computers it's red, green, blue, but in reality our primary colors are yellow. So let's take yellow. Yellow. And our yellow equals let's see, 4, because those are our primary colors. Now you remember that for your primary colors, if you mix them you get a different color. For example, if we had blue and red, right? If we have blue and red, it makes what? Purple. So let's take purple. And purple equals, let's say we add, all we have to do is add blue and red, and we get 3, right? So let's say we have blue and red, which is 3. And let's take blue and red, which is 3. And if you take red and yellow, it makes orange, and so orange. And if we have orange, red and yellow make orange, we add those two together and it gives us 6. So we do 6. And if we take now blue and yellow, they make green, and that will make 5. So let's put them in order. Let's say green is 5. Int green equals 5. Because we take those. And you may be wondering what in the world I'm doing, but I am going to show you something that might make sense. I think I will. So we take that. So we have 1, 2, 3, 4, 5, and 6. And you say, well, those are just values. What is that? That doesn't mean anything. But if we use the binary OR operator, we can join this value. So I can say my color, right? So I can say my color, printf, and I can say my color. I want my color, if I combine blue and red. And I could simply add them together, right? I could definitely add them together, but I don't want to do that, right? So let's go ahead and do that. And I have my color and my color. And what I'm going to do is I'm going to combine several colors here. So I can combine blue and red. No, did I have the right? Blue and red should make purple. So blue and red. But I'm not going to just add them together. That's not my intent. I don't want to add colors together because I want to be able to combine them. And the way I do that, I use the OR operator. Okay, the bitwise OR. And what that does, that joins them together, but it doesn't necessarily add them together, because if I said blue and blue, it doesn't add blue and blue. It doesn't take blue and add two and make it red. It's not going to do that. So if my color is blue, so if I say blue and blue, excuse me, sticky mouse situation. Oh, I can't stand this mouse. Let's see, blue and blue makes, and we can say something like this, %D, and we say blue, and this is a bitwise binary OR, because we're joining them together and say blue and blue or blue, right? Because we don't really want to join them together. We want to, you can store the value of those two ORs, and I'll show you how it does that. And the reason that I'm doing that is because the binary OR, for example, the way it works something like this. It takes a value, and if I have 1 and 1, and I have 0, 1, 1, 0, what the value does is wherever it finds a 1, it'll put a 1. So this is both zeros, and in this case, this and this is a 1, and in this case, this and this is a 1, but it's not going to add them together. It's just going to say, oh, that's a 1. In this case, it's going to take those two values together, and it adds also a 1. That's the binary OR. If, in other words, a binary OR, if a 1 is in either one of the two values, then it ORs it. So you notice this combined the number 3 with the number 6 to make the number 7. It did not add them together. It took the value 3 and the value 6, because this is 0, 1, this is 2, and this is 4, and this is 1, and this is 2. So you have 6 and 3, and they make 7. That doesn't add up. If we were to add them up, it would give us a totally different value. We don't want that. We just want to combine the two colors. These two kind of cancel each other out, so they just become one. They just don't become that. So what will my color blue and blue make? So let's take a look. Color blue and blue makes 1. Oh, it's still blue. But if we were to do this, what if we said my color blue and red make? What would you expect that to make? I think you know what blue and red make. But let's see if it does make red. And blue and red make. Blue and red makes 3. What is 3? Well, 3 is purple. Look at that. Okay, well that's no big secret there. But what if we took purple and yellow? Ooh, that's an interesting color. We haven't even considered that. But let's just say that if we combine blue, red, and yellow, they make the color brown. I don't know if you knew this. It's an interesting thing, but yes, if you take tempera paint and you combine blue, red, and yellow, they will make brown. So let's take brown, and since we know that it takes blue, red, and yellow, blue, red, and yellow to make brown, so we take 1, 2, and 4, and that's 7. So we have 7. So let's take, what if we make, let's combine those colors. My color blue, red, and yellow. Blue, red, and yellow makes, and then we can, let me slide this over so you can see, or better yet, let me bring it down and tab it over and bring this back a little bit. Blue, red, and yellow makes what? Blue, red, and yellow make 7. Make 7, which 7 is brown. What do orange and brown make? Oh, I didn't have green. Let's see, green. What do green and yellow make? See, green and yellow, if we, well, they'll make something interesting. Green and yellow, I don't know what they'll make, but we could find out. But let's take, for example, another color. If we took those colors, so you get the idea. If I combine them, I get all these different colors, and they'll fall into one of these values. Notice that my primary colors were all in the different order of the different significance digits, right? So blue is 1, red is 2, it doubles, right? And then yellow is 4, so they double. Those are my primary. Everything else is a combination of those other values, so we can combine them. So let's say, for example, that we wanted to store the value, and I wanted my color, right? And I wanted my color to be blue. My color equals blue, and we don't add them, we OR them together. And I wanted my color to be blue and red. Let's just say blue and red. Well, I need to know, does my color contain blue or red? So I can say something like this: printf I can say %D. And how do I find out if my color contains red? And I can go like this. And I can test for the condition, and I can say my color contains red, and I can say my color. And in order for me to test if it has color, remember, we go back to the AND. So if it's true, it will take those bits where they join together, where blue and red meet, which would be in the 1. It will give me blue, but it depends if I'm testing for blue. If I'm testing for blue, I can test for blue, and I would have to pass it blue. But if I'm testing for red, I have to pass it red. And so I could say my color contains blue or contains red. Maybe I have it wrong. Okay, let's see. My color contains red. I want to see if red is contained in my color, and I can say and my color in red, right? Because I have my color, which I would have my color, which is my color blue and red, are going to make blue and red are going to be 3, and the number 3 can be represented like this: 1 and 1. And the number the red is 2, so it's like this. So it's going to take and compare, and let's add the 0 just for clarity. It's going to compare these two, and it's going to find a 0 in the 1's place, but it's going to find a red in the 2's place, so it's going to give me 2, and 2 is red. My color contains red. I test it for red, see if my color contains red, and I run it. My color contains red too, so it is red. If I wanted to test to see if my color contained blue, I can do test it against blue. And this time, I use the color blue to see if the color blue is contained within, right? And I run it. And I could do the same thing even if I had another color here, like if I added another color, and I can say orange. Let's say I add orange or I add yellow, and now I have all the colors in it. My statement will still be true. It doesn't matter that this changed. It'll still tell me that it does contain blue and does contain red. And that is your bitwise OR. So you combine the AND to test it to see if it has the value. You store the value like this to combine it. But you don't want to add the numbers, because if you add 1 and 2 and 4, yes, they're okay. They're going to give you 7. But not when you do, for example, 1, 2, and 3, because that's going to give you 7. That's going to give you 6. And we know that red, blue, and purple don't make, what is 6? Orange. That's not going to make orange. So You don't want to just simply add them. That's where you use the bitwise OR. So let's take a look at another one. And I don't think I'm going to be able to do all of them. Now the binary OR is very similar, and you can imagine what you can do with binary ORs. Binary OR, for example, if you have 0, 1, right, and 0, 1, that this is going to return false because this binary XOR is exclusive OR, which means that it has to be in one or the other, but not both. 0 and 0, it doesn't have one. 1 and 1 has it in both, so that doesn't. It would have to, in order for this to return something, it would have to have, for example, 0, 1. No, wrong. 1, 0. And now it would actually result in 1, 1. Because if you take the binary OR, what you actually have is this, and it gives you this, right? So you have this, and exclusive, oh, not that, but you have this. And you can run these tests. I leave that as a challenge to you to test these values. And in this case, you have this or this. And that's a way to check to see if you have any intersections between two numbers. So for example, if we wanted to test that the colors were totally separate from each other, right? Like, for example, there was not a mixture of blue and red, we could do that. We could make sure we could see that it didn't have it, right? And we would know that there's no, it would have to return all zeros so that our color doesn't have, and we could do that and test to see if it has that. But if it gave us a different value, then we would know it has it. So for example, if we change this to this, what would it give us? Right? So it would have to give us all zeros to know that they're not, the color is not contained within it, but it gives us 6. So we know it's not, we know there's something going on there. So we know if it didn't give us all zeros, that means there's some same attributes in that color, right? So we have that by the exclusive OR, and I won't talk about the complements, but I will talk about another one that's important, and that's the bit shifting, binary left shift and binary right shift. That you may not know about this, but if you shift a number, and let me see if I get it right, printf %/n, and let's take some simple values. Let's take 1. Let's take 1. Let's take the value 1 and shift it 2 positions to the left, right? So if I take that and it gives me %d, and I say 1 shift 3, I think I do it like this. Let's see if it works. You notice that it converted my value, my number 1, to an 8. Well, why was that? It's because what it did, it took this number 0, 0, 0, 1, and it shifted the 1 3 positions. So it shifted 1 position here, 2 and 3, and it positioned it, and now the number becomes that. And you could take whole groups of numbers and shift them, and it's really quick way to do multiplications of 2's and stuff like that. So if I wanted to multiply a number times 2, okay, for example, if I took the number and I took the number 4, if I took the number 4 and I wanted to multiply it times 2, I would just do shift 1. Right, so if I take shift 4 and shift it one place, it should give me 8. So let's go ahead and try that. And when I shift it one position is 8. If I was to shift it, for example, 2 positions, it would be like, it would go from 8 to 16, right? So it would be like, so it would be 4, and then it would be 16. So if I shifted 2, it would become 16 because it's moving. And you get the idea there. The right will do the opposite. So the right will the shift right If I take 1, and I don't want to take 1, but I want to take a big number. Let's say I take the number 8, 0, 1, 2, 4. So if I take the number 0, 1, 2, okay, no, wait a minute. 1, 2, 4, 8. So if I take the number 8, right, which is the number 8 is this number, and I want to shift it all the way back. Well, I want to shift it 3 places. It should give me the number 1. So if I go 8 and I shift it 3 places, so I go take 8, shift it to the right 3 places, it should give me the number 1. If I take, for example, the number 16 and shift it 1 place, so let's take 16, it's going to cut it in half. So if I take 16, shift it 1 place, and you notice I'm taking even numbers of the that only take up one bit to have the value, because the number 16 would be actually, it would be 1 0 0 0 0. So I'm just taking 1 to demonstrate the example, but you could really do it with any number. So what it's going to do when you shift this way, it becomes 0 1 0 0, and that number is 1 2 4 8. It becomes 8. So let's go ahead and run it, and it becomes 8. There it is. That's my tutorial. There's more. If you want to learn more about it, I'm going to provide some links where you can get more information. It becomes very useful when you start doing really optimized code, or when you want to have different options. Let's say, for example, like in the case where we wanted to have both blue, red, and yellow, we wanted to have another color, and we want to provide those options. We can easily store that in a single byte, or maybe a int. What if you wanted to know if something was blue and if something was yellow? You can pass one single variable and have all those values stored in it, and it becomes very useful for a lot of different options. Now, you keep in mind that an integer is 4 bytes, and so that means that you can store a lot of information, because 4 bytes is 32 bits. So can you imagine what you can do 32 bits? We use an example here of only in this case, we only use an example of not even a whole byte. This is just a nibble. It's just 4 digits. But can you imagine if you have a whole 32 to play with? You can have a lot of different options, all stored in one value. And you just check, you use them as flags. So is this flag on? Is this flag on? Then we have that. And you can see where that becomes very useful.